Hello good people, I'm going to talk about element blocks in the periodic table. The humble periodic table of elements contains a certain internal logic, and the table can be used to provide a lot more information about the elements than I previously stated. The periodic table can be divided into element blocks, and the element blocks give information about the type or shape of the orbital that the outermost electrons are going to occupy. So, what are these blocks? Starting on the left, we have the S block elements. Note that the helium, which is all the way over here on the right with the noble gases, is also an S block element. What does it mean to be an S block element? It means that the outermost electron will be in an S orbital. The next element block is the P block, over here on the right-hand side, highlighted in green. The outermost electrons of all of these elements will end up in a P orbital. The next block, highlighted here in blue, is the D block, and this includes the transition metals. So the outermost electrons of the D block elements will end up in a D orbital. And finally, we have the F block, and it is highlighted down here in orange. The F block includes the lanthanides and the actinides. So the outermost electrons of the F block elements will be in an F orbital. This is not where the story of element blocks ends. The periodic table can be used to give me even more information. Not only can I use it to determine the type or shape of the outermost orbital, I can also use the periodic table to determine the principal quantum number of the outermost orbital, as well as how many electrons will be in that orbital. How does that work? The period numbers can be used to determine the principal quantum number, while the rows in the individual blocks can tell me something about the number of electrons present there. This works really well for the main group or the representative elements. So let me get rid of this and bring in the condensed version of the periodic table, the one that contains only the main group or the representative elements. And here it is. Let me highlight the element blocks again. So now that I have removed the transition elements as well as the lanthanide and the actinide series, the only blocks I am left with are S block in red and P block in green. I'm going to look at nitrogen first. So up here is nitrogen. Nitrogen has 7 protons, which means in its ground state it has 7 electrons. Over here on the left, I'm going to write N, and now I'm going to write the electron configuration. However, there are already some things that I should be able to determine from the periodic table. Firstly, the outermost electron will be in a P orbital. So over here, I'm going to write P. Nitrogen is in period 2. This means that this P orbital will have the principal quantum number 2. So I can write that as well. Finally, nitrogen is in the third row of the P block. So 1, 2, 3. This tells me how many electrons will be present in this outermost P orbital. So there will be 3. So now I know where my electron configuration needs to end. It needs to end with a 2p orbital and 3 electrons being present there. So now I need to write in what comes before the 2p orbital. Well, I will have the 1s orbital and it will have 2 electrons. Then I will have the 2s orbital and it will have 2 electrons. Alright, so this looks a little bit squished, so let me quickly fix it. There we go, that looks a little bit better. Okay, let's do another one. The next element I'm going to look at is neon. So here is neon, it is a noble gas. In its ground state, it has 10 electrons that I need to accommodate. I'm going to write Ne for neon, and now I'm going to use the periodic table to once again determine the last orbital. So the outermost electrons will be in a p orbital, so I can write p already, Once again, I'm in period 2, so the principal quantum number is 2, and I'm in the 6th p block row, so there will be 6 electrons there. So I can write a little 6 up here. And now once again, I just need to write what comes in before. It'll be 1s2, 2s2, and then 2p6 at the end. All right, let's look at a metal. So now I'm going to pick magnesium. So magnesium in its ground state has 12 electrons. I'm going to write the symbol for magnesium, Mg, here we go. And now I'm going to use the periodic table to tell me something about the electrons in the outermost orbital. So magnesium is an s block element. So its outermost orbital will be an s orbital. It is in period 3, so the principal quantum number will be 3. And it is in the 2nd row of the s block, which means this s orbital will contain 2 electrons. And now I need to write what comes before. So I will have 1s2, 2s2, and 2p6. Let's do one more. I'm going to pick chlorine. Chlorine in its ground state has 17 electrons. So here's the symbol for chlorine, Cl, and I need to accommodate 17 electrons. Where will the outermost electrons be? Well, they're going to be in a p orbital, because chlorine is a p block element. Chlorine is also in period 3, so the principal quantum number will be 3. Chlorine is in the 5th row of the p block, so there will be 5 electrons there. So now I need to fill in what comes before. I will have 1s2, 2s2, 2p6, 3s2, and finally 3p5. Keep in mind that this approach works really well for the main group or the representative elements, or if you like, for those that belong to the S and P blocks. Once we start looking at the D block elements and the F block elements, things get a bit more complex. I know, you are very surprised, but hey, this is chemistry. For every rule, there is a list of exceptions as long as my arm. But even those exceptions have certain rules. So how does this work for transition metals? Well, let me bring them back in. Alright, so the periodic table is now at its full strength, and I'm going to look at titanium as an example. So here's titanium. It is a transition metal. It is a D block element. Let me write out the electron configuration for titanium. So Ti, that is the symbol for titanium, I need to accommodate 22 electrons. Titanium is a D block element, so the outermost orbital will be a D orbital. What will be the principal quantum number of this D orbital? It would be really nice if it were 4. After all, titanium is in the 4th period. However, now that we are dealing with D block elements, our rule needs a slight modification. Now the principal quantum number of the outermost orbital is the period number minus 1. So the period number is 4, minus 1 is 3. So this orbital is a 3d orbital. How many electrons are there? Well, titanium is in the 2nd row of the D block, so I will have 2 electrons. And now, as before, I need to write out what comes before. And I'm going to do that quickly. And here it is. Now you might be wondering what is going on here. Why is it that I have 4s before 3d? Recall that each orbital has its own energy level. And as we go higher up in the principal quantum number, we cannot use the principal quantum number alone to determine which energy orbital has a higher energy level. The 3d orbitals are in fact higher in energy than the 4s orbital. Okay, so for the D block elements, I need to watch out for the change in the principal quantum number. It is not the same as the period number. Unfortunately, this is not the only way that D block elements misbehave. Let's look at copper. So copper is here, circled in yellow. In its ground state, it has 29 electrons. So let's use what we have learned so far. what would be the outermost orbital for copper and how many electrons should be there? So I'm going to write the symbol for copper, Cu, and now I'm just interested in that outermost orbital. According to the rules that I have presented so far, the outermost electrons of copper should be in a d orbital. It is a d block element. So I'm going to write d. What should be the principal quantum number? Well, copper is in period 4, but I remember my little change of the rule when dealing with d block elements. I take the period number and I subtract 1. So 4 minus 1 is 3. So this d orbital is a 3d orbital. How many electrons should there be in this d orbital? Copper is in the 9th row of the d block, so logically I should have 9 electrons there. Unfortunately, this is not the case. As it turns out, things look a little bit different. The outermost orbital is a 3d orbital, but it does not contain 9 electrons. It actually contains 10 electrons. And the preceding 4s orbital does not contain 2, but only 1. The reason for that is outside of the scope of this video. Now, before you shut down your device in disgust, let me assure you that there are sub-rules that explain this behavior as well. As I said, this is science, not magic. We are not going to go into these sub-rules, but they are there. For now, keep in mind that these rules work really well for the s and p block elements. That is all for now, and I will see you on the flip side.